Hello everyone, Aaron here and welcome back to Leetcode. Today we are doing the power of 4 problem. Given an integer n, return true if it is a power of 4, otherwise return false. An integer n is a power of 4 if there exists an integer x such that n is equal to x, 4 to the power of x. So here we say 16 is 4 squared, 5 is not a power of 4, 1 is 4 to the power of 0. So that's those. The reason I'm doing this one in C today rather than Python is because I don't want to do it the obvious way. I don't want to try and take log 4 and then check that's an integer or very close to it. I don't want to continually divide by 4 and see if I ever get down to 1. Or anything like that. What I want to do is I want to think about how 4 is represented, or powers of 4 are represented on the computer. So obviously every number is a binary number on a computer in one way or another. So 4 is 1, 0. I'll write them like this. Now these are 32-bit integers, so in fact there's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30, 31, 32. This is what a 32-bit integer of 4 looks like. What about 16? Well, it turns out 16, in fact, we'll do the first power of 4, which is of course 1. 1 looks like this, 4 looks like this, 16, what does that look like? Well, a 16 looks like, sorry, no, that's not a 4, that's a 2, good grief. 1, 2, 4, that one is the 4, so this one here, 1, 2, 4, 8, 16. The next power of 4 is, this is 0, 1, 2, 4 to the power of 3. That's 4 times 4, which is 16 times 4. 16 times 4 is 8 times 8, which is 64. So the next one is 64. And if I just quickly steal this, what it actually is 1, 2, 4, 8, 16, 32, 64. So what we can see here is that it's the powers of 4 have exactly one in them, and it's in the 1st, 3rd, 5th, 7th, etc., etc., etc. slots up this binary representation. The quirk is that they tell us the number can be negative, but the good news is that powers of 4 are always positive, because no matter what you set x to, 4 to the power of x is going to be a positive number. So, if n is less than or equal to 0, return false. There is absolutely nothing we can do. Else, what we want to do is we need to do this check. What's the way to do this check? Well, first off, how can we check that there's exactly 1 bit set somewhere? We don't care where it is at the moment, just that there's 1 bit set. And the way we do that is if we think about what, well, let's say what this looks like if we take away 1, for example. This looks like a 0. So it's all zeros. If we take away 1 from this, these two turn into a 1. And so we see that this is all zeros down to here, and this is all 1s. And the idea is that if we say, let me do this with a much smaller number, a much smaller number of bits. Let's do 4 again, but this time only with 3, 4, 5, 6, 7, 8 bits. So 4 is this one. 3 therefore looks like 0B, 1, 2. That's a 3. 4 and 3. Yeah, 4 and 3 is going to look like, I need to space these out even further. 0, 0, 0, 0, 0, 0. But what happens if we had, say, 2? A 2 looks like 0B, 0, 0, 0, 0, 0, 0, 1, 0. If we have 3, 3 and 2, 0B, 0, 0, 0, 0, 0, 1, 0. 3 and 2 is not 0. 4 and 3 is going to be 0. 3 and 2 is not going to be 0. And actually this trick here is true for all powers of 2. So I know we're doing powers of 4, but all powers of 4 are also all powers of 2 because 4 is a power of 2. So the idea is that is power of 2. This is if we take n and AND it with n minus 1 and check that that is equal to 0. If that's true, then we know it's a power of 2. So that means if it's a power of 2, the powers of 2 are all of these, but they're also all the ones with this skipped bit filled in as well. So all we want to do is return is power of 2 and correct bit is set. So this is where we need to check that it's the correct bit set. So we want to do n and we want it to be, we know n only has one, hang on. I'm saying this badly. Let me try this again. So if this then we know n has exactly one bit, else return false. So now what we want to do is we want to check whether that one bit is in the right place. So the right places is 0, the binary representation of, well, hang on, what's the largest one here? I'm just trying to work out whether this is going to be a, oh, hang on, let's do 1, 0, 1, 0. Oh god, this is a very long way of doing it. Hang on. Let me do the octal version. 1 in 0, 0, 0 is 1. 4 is 0, 0, 4. 16 is 0, 0, 1, 0. Oh, good grief! This is difficult. Hang on. Let me just stick a 0 on the front of this. That's 1, 2, 3, 4, 5, 6, 7, 8, 8, 16, 24, 32. if n and right places, if we look in all the right places and we see something that is non-zero, return true, else return false. Ha. This thing's gross, and I'm not 100% sure that's valid C syntax. Let's find out. Apparently it is valid C syntax, excellent, and this seems to work. So let's use all the example test cases. Excellent, works for all of them. So 1 works because we showed this up here. 1 minus, well, it's positive, so we pass that check. 1 and 0 is 0, so it has exactly one 1-bit set. And then the 1 lines up with this one here, so it's got the 1 in the right place. Before we go any further, this can absolutely be tidied up because there's only one happy path. And that happy path is when n is greater than 0 and n and n minus 1 is equal to 0, and when n and right places is greater than 0. All of that logic there is here. It's a power of 4 if it's positive, and it's a power of 2, and it's one of these specific powers of 2 that we have all ordered together. Let's just double check that still works. To really compact this down, you would probably work out what this is as an integer, and then just put it in line here. But it's fine as it is. Let's hit submit, see what happens. Pretty fast. So this is obviously well too low for it to actually make any meaningful measure of its speed. Basically, this runs instantly. Its memory use is absolutely par for the course, but that's expected. Almost every solution is going to be running in approximately the same amount of time. So sorry for the slightly dodgy explanation, but hopefully that made sense. It's quite a cool little program, this one. All it does is some bit shifting, and it can immediately tell you, without any loops at all, whether a number is a power of 4. That's it from me for today. Thank you very much for watching. Remember to like, comment, subscribe, all that good stuff. Let's make the YouTube algorithm happy, and I will see you next time. Bye.